tutorial means I have here some simple Cosy input files. I will run them, I will show to run them, and I encourage you to run them yourself, because some of the questions that you have, I may have too. And what I do, I just take a simple code, run it, and see what the system does, instead of going through mathematical calculations of matrices and who knows what. That is often a practitioner's quick answer. So anyhow, you will eventually see the complete code of a Rickert separator, St. George, or the SECAR, and you will have to understand what this means, what you want to change, what questions you have to the system, what you can answer with the code. So you need to know the code. So that is the purpose of this. So Cosy for Infinity is a modern iron optical code, arbitrary orders, written by Martin Wirtz, here a professor at MSU. You registered, you have the system running, very good. Oops. The lecture 1 introduced you to the formalism, but now you will see how the code really runs. And this is an example. So you have on the wiki, you have example, and Cosy input files always have the extension .fox. They are basically text, but without extension .fox, Cosy doesn't recognize it as an input file. So this simple code here is to calculate the transfer matrix. In first order, we call it matrix, and in higher orders, a map, because it's a higher order transfer function for a quadruple doublet. Now, Cosy include, you have to have the right path, of course, and that depends on the platform. I'm running here Cosy 9 on Windows. You may have done something else, as long as it runs. Then everything is called a procedure. The inherent main procedure is run, end procedure, then you run it, and then you end the code. And everything in between is what you tell Cosy to do. First, you need a definition of which order you want to calculate. The first parameter. Oh, you cannot see it big enough. Is this big enough? You mean this? Yeah. Then you see it big. I'm a little bit worried, but maybe we don't see the other screen then, but let's just try. Okay, so you see now, at least this step we are okay. The next step maybe. Okay, because I really wanted to run the code and explain things to you. Anyhow, this is a Cosy command. It defines the order of the calculation, so you can say calculate only in first order, in second order, in third order, and whatever you want. Typically, you don't want to go beyond 6 or 7 order. The second one is a phase space. If you give here a 1, then it calculates only the horizontal plane. So the number 1 or 2, x a or x theta, you know now what that means. If you want to calculate the vertical, also the y theta or yb, sorry, then you need here 2, which we don't here, so it's a little bit overkill, but it's just allocation of space. And if you want to calculate energy or momentum or timing, then you would need here 3. 0, there are some additional parameters you can define. This is for a later day. This here it defines the particle that you are having. The first one is kinetic energy, 10 MeV in MeV. The second one is the mass and the charge. And so you see this is an alpha of 10 MeV for this example. Then you start with a clean unity matrix in order to prevent that for some reason there was something loaded and you are confused what matrix you really have. So it sets to the unity matrix. Then you define the elements, a drift of 0.1 meter. You cannot see the pointer. Oh, yep. Thanks for that. Now you can. So you obviously understood this far, but now it's getting more tricky. So here's the drift, 0.1 meter. Cosy uses meter as unit. Everything is in meter. This is quadrupole. MQ is a quadrupole. And I've written here the length of the quadrupole, of course, is important. The field at the pole tip. And it says here aperture, what Cosy means is the radius. So it's not the full aperture, it's a radius. So everything is relative, input parameters, whatever, relative to the central ray. So if you have aperture, it's not the diameter. It is half the diameter, the radius. A drift and another quadrupole, and you see already here, it has a minus sign, the strength of the quadrupole, or the field at the pole tip, and that's a defocusing quadrupole. And then you have a drift. And then we want to see some output. So we see the transfer matrix on the screen with the print matrix or map. And you can have also in a file, as in this example. Now comes the tricky part. If I reduce this, I hope so. I think.
Now we have to switch to the duplicate. Okay.
No, this is not what I need to see. I need to see the.
You just try to be smart. That's the problem. Yeah, but it's not duplicating the right thing.
No.
You press escape. Ah, okay.
Okay. So I have here in my directory Cosy 9 running, and I have example 1. This is the Fox file, Cosy script. And first I want to open this. No, sorry, that is not. I want to open this to see what I have. Open with a notepad. So you see the same thing as in the presentation here, but now this is the input file, and I can run it from here by saying Cosy, and I run it, and you will probably do something else to run. And if I take example 1, then you see the execution of this file. And it shows immediately that the higher orders included. If I would change, just to give you some practice and may want to play yourself, if I change the order to 1, say File, Save, and I go to the execution window, say Cosy, the same program but now modified, it shows only the order 1. Okay? So here are the matrix elements, and I will go through the definitions of those. It's right now a little bit cryptic, but you will soon see it relates to what you know already. Let's go back to order 3. So now you see the first order elements here, and I recognize them because here in that last column, you have only parameter 1. Here you have always 3 parameters. Always the sum of these is 3, so these are third order. There's no second order because a quadrupole in itself does not have, if symmetric and not special multipole designs in it, it has no second order. And I will probably next lecture you will see why this is physically, but for now just take it, there's no second order in a symmetric, well-designed quadrupole. So now we have to come to the meaning of these parameters. Well, before the meaning, okay, coordinate system. The Cosy has 8 input parameters, and they are called X, A, Y, B, the L, which is a time or the length difference, then the energy relative to the central kinetic energy, then the mass changes, and theta. So there are 8 parameters. A beam definition you know by now. I gave an example for the alpha of 10 MeV. Here are the length is just dl is the Cosy command, and then you give the length in meter. So 0.1 we have in our code. And this comes from the beam book. There are a beam documentation, and there is a programmer's documentation. These commands are in the, and I think we have it on the wiki. If not, you probably downloaded it for yourself. So you understand the syntax. It's always well explained here, and you have to look at these parameters. So we use the command MQ, which defines only a quadrupole, length, pole tip at the aperture, which is the radius. If you want a multipole, which for instance, Sekar has in the first quadrupole, it's not only a quadrupole, but it has also a hexapole for correction. Then you need the M5 command, you will see it there, and then you can define here the different multipoles, quadrupole, hexapole, octupole, decapole, and duodecapole. That is it. Now comes a little bit, well, tricky part, if you want. These matrix elements that you saw are actually defined as follows. The columns here define at the final coordinate of X, A, Y, B, and L, and no dispersion here because there's none in this only quadrupole. Dispersion you need a dipole for, as you probably know by now. And these are the initial coordinates. So this here would be the initial coordinate X and the exit coordinate X, so the magnification. The second term here is again X at the initial A. So X initial coordinate, A the exit coordinate, and so on. So the focusing function XA or R12 would be this here. So this is here at the initial coordinate, the angle, second parameter in this notation, and the first. So we see here we are not in focus, okay, in first order. And then you have all the higher orders here. So what changes in third order? Of course, you have to change 3 parameters. So 3 times the entrance X, XXX, so dx, you can think of it as a differential, or, and then you have this term. And if you look here, you have the different terms here. Is this clear to you? Or questions? Say again? B2? This one here? Oh, this defines which initial coordinate this matrix element has. Every matrix element has an initial and a final, as you know. Magnification XX, you learned that. So that you still here. So this X is the initial coordinate. The matrix element from the initial coordinate to the final coordinate, X. This is this term, and I replicated that here. So this here is defining this element. Yes, that's the third order. If there will be second order, which we don't have a quadrupole, there would only be two. So a second order means you change two parameters at the same time, or the Taylor expansion with two terms. Third orders, they must have three terms, and fourth order, four terms. If you think about this as the Taylor expansion coefficient, then you see, you know what that means. So there could be an X. So there's an X to the third element here. So X to the third, at the entrance X is this term, and that is the Taylor term, this coefficient, which I'm just pointing at. Can you see? Yeah, this I'm pointing at, times X to the third, Taylor expansion. Okay, I think you have to look at this a little bit in a quiet moment and do that several times. And it's the most compact way to show the whole matrix, but it's a little bit tricky to wrap your mind around it. Okay, so one more confusion is, you see the XA, which is R12, which is a focusing function, is here the second term. So the 0.69 tells me it's not zero, so we are not in focus. It goes here in the column. In the matrix which I showed you in the formalism from this, they actually column and are reversed. So you need to make sure you know what, and when you see the dispersion, then you will see, which we don't have now, but later when we have a dipole, then you can calibrate yourself which is which element. Does that answer your question? Okay. So you need to look at this a little bit longer than we have here to find out which element is what. Okay, so now we have printed out, okay, another thing is, it is in the directory where you calculate, there's a file, and that is a Ford, file number 11. So if you open that, open with the notepad, you have asked the program in that last command to print it actually in a file. So if you see it on screen, but you need it somewhere documented or used somewhere in a spreadsheet or so, these elements, then you want to send it in a text file, and that is here. Okay, it is this here, and the command that you used, the command to plot that out is here, PM11, which prints it out to Ford 11 file in the directory where you are working. So now you want to, now you have the matrix element. Now you can already calculate up to arbitrary order for a system, a quadrupole, doublet, you can already calculate the matrix elements. Whatever this is used for, but you can do that. Agreed? So now you want to see the rays. Now we take that example 1 and we add a few commands, and these are the SB. These define the beam and the maximum extent, and the ER command says how many subdivisions are there. So here you have 0.15, so 150 milliradian roughly, divided in 5 rays. And the BP command says, after you define the rays, begin the picture of the rays with these commands which you just learned, and then you say end. You may want to end somewhere in the middle or at the end. Here we are looking at the end. And we need to give some plot commands. In PG -10 -10 is for Windows to make a plot, and you may use some other commands, so that's specific on your platform. So that is added. So if you go now and run Cosy and say, we're not running example, but we're example plot, which executes this file that I showed you, then you get this, and you have a plot. So in addition to, of course, all the matrix elements, you have here the 5 rays, plus or minus 150 milliradian, and you'll see roughly the extent of the radius. And you see that with this radius, the particles go through the first quadrupole, but they're hitting the wall in the second. So this is you learn already with this one. So, example, and you may want to run this yourself now or at any later moment. There's a list here of what you learn, and I just roughly told you something, but there are more questions you may have, and you should be able to all see that. Oh, the vertical one is, the horizontal one is this, and this is a vertical one. One thing you also see, this edge is vertically, this quadrupole is vertically focusing, this is vertically defocusing, and this is vertically defocusing, vertically focusing. That is, since I didn't finish the first lecture completely, you will see that next lecture. This is a property of an ion optical quadrupole. One quadrupole itself is always focusing in one, defocusing in one direction and focusing in the other direction. Not like a lens, which you know from optics, which focuses in both directions, vertically and horizontally. So that is a complication of a quadrupole, and you need actually 2 quadrupoles to focus, because one will always be defocusing to infinity and the other may be focusing. So that was not done here. This was just some arbitrary strengths. But if we go now and look at, what was this? Example, which is an example? And I encourage you to go to the tutorial, and so this one is example 1, focus. Let's just run it. So if I prepared a file, example, oops, that wasn't what I wanted. Example 1, focus. So now you see I changed the strength of the quadrupole here. These are the strengths that we had before was not strong enough. So now we have a pole tip strength of 1.2 Tesla, minus 1.2 Tesla roughly. And now the system is focusing in both directions, horizontally and vertically. That is needed. So 2 quadrupoles are needed to focus in both directions. Otherwise, one direction would not focus. Now, you see also that the strength is too high. Quadrupole with 1.2 Tesla is high into saturations. We don't have that in recoil separators. If you're interested in the high resolution spectrometer, which goes to 8 Tesla meter rigidity, you will see that we have superconducting coils and we're going in high order, big time. This is not possible for a precision instrument like SECAR. And so this is out of the realm what SECAR would be useful for SECAR. So you need some knowledge about the hardware before you can actually use the software, the point I already made before, because you may run into a specific problem in the design. Now, the good news for you is if you're using SECAR, the system is already designed. So we have already taken care of all these problems, but there are others left. So, and this is in first order. Now I show you something interesting. I take that file, example 3, no, example focus, and open it. Open with a notepad. What is the time? Yeah, we still have time. So I had calculated this in first order. Now let's change this to third order. So if you go to third order and run it again, now you see what was a nice focus here horizontally, a nice focus here vertically, is now affected by higher order. You see also here what I explained in one group who was asking about how, I think, Sarah, did I do that there, or the other group? A hexapole, there's no hexapole here, which would take for the small rays. Look at this here. The small rays, they focus here. What do, if you open up the angle and attract the higher orders, what would happen? Here, the focus shifts. So this is a third order. If there would be a second order, the larger rays, the larger angular rays, would not refocus along Z, but they would move to one side, either the left side or the right side. That would be then in the focal plane of a spectrometer, if you would look there, a C shape. This here would be an S shape. Now you have to go in your mind to this here a couple of times to familiarize with yourself. I've done that many times, but this is how you have to look at this to understand these higher orders. So, of course, plus minus 150 milliradian is a huge opening. You don't have that with SECAR. With SECAR, you have a smaller 25. Is that what we our design? Milliradian. So I could now, if I make this here, now let's just play for a couple of times. Instead of 150, we say we open only 25 milliradian, file save, and we run it. Oops, that didn't, oh, that was only horizontally. Okay, so you say horizontally it's still bad because you didn't take care of the, let's do the vertical. That may give you a little bit easier to see example, save. No, didn't. Oops, I changed the position, not the, yeah, you have to keep track of which parameter you're changing. So you have to know your commands. Yeah, now you see we reduced the angle here, which was 150 milliradian to 25 milliradian, and there from the eye, you say already a focus. Now, if you want to have a system which all what you see and plot at changes of 1%, you don't even see. But some of the system, like the mass separation in SECAR, has 10⁻⁴ precision. So it's not good enough to look at this nice focus, what you say, but at 10⁻⁴, you need to plot out the numbers and do some calculation just to give you an idea. So we have played with this here, and you see now, if I have a question, if you have a question, you ask me, and if I can answer. If I have a question, there are not too many people I can ask, but they either don't have the time or not the expertise, mostly not the time. But then I take Cosy, run it, and answer the question that way. Before I go and multiply matrices, etc., etc., that is not possible nowadays. So Cosy is very important for you to learn and to set up a system, etc. So you have learned a little bit here. Now let's go and see what else we have. A triplet. Oh, yeah, this doublet, I still need to show you. What you see here is the angle here is 25 milliradian because we put it in, but the angle here is much larger. So there's an angle magnification, and that corresponds to a spatial magnification if you have a focus. It's not a one-to-one image. So if you would take an image and you put it through a camera, you see exactly the same proportion. This would be in one direction or the other direction squeezed with the quadrupole doublet. With a quadrupole doublet, you cannot do more. If you want a one-to-one imaging where the angular magnification, the spatial magnifications are all one, so that you have a one-to-one image, it is called, like a camera would do. You need a triplet. So let's look at what we have here is triplet. Third order that we had, triplet. This is the triplet example. So I added here another quadrupole and something else. Yeah, I use now a subroutine. So instead of defining in the main program, I defined a procedure called triplet with 2 parameters. It's a symmetric triplet. The first and the last one have the same strength or gradient. And the middle one is A, and it's defined here. So you can parameterize this. So this gives you another insight what Cosy can do. You can define parameters, you can make subroutines. The subroutine triplet ends here, and in the main program, which is the same what we had before, instead of now writing the whole thing, I just write here the subroutine triplet with input parameters, which are here defined as 0.5 as initial parameters. So let's just run this example 2 and see what we get here. So here we have now the triplet, but it is not set to have this one-to-one imaging as we had hoped for. So we need to change the strength. So you can now go and change the strength by hand. If you're experienced and you know what you're doing and you look at these images, then you can probably get pretty close by changing it by hand. And that I have done here. And you see now we have a, is it big enough, Fernando? I hate to go in the other mode because then I cannot run the program anymore. So you have here, you see the angle here, the angle there is the same. The angle here and the angle there is also the same. Now, you have the problem if you're not experienced and this takes too much time for even if you are experienced, then you can run a fit routine. And the fit routine is, which one is it now? Example 3. I think it's example 3. And now have a look. This program is fitting, and it's not for the triplet, but for the doublet. So you have that. You can of course not do better than the theory allows, but you have now a focus here, and what you would be doing for half an hour, the Cosy can do for you. Now it's an example 3, and if you open example 3, then you see the additional commands. Example 3, let's open that and briefly discuss. Open with Notepad. Okay, so here you have incorporated a fit routine. Now you fit the Q1 and Q2, which are the 2 parameters of the triplet, and you plot it. Of course, if you have a complicated fit you don't want to plot, I just do that for your demonstration, that you see how the program is doing something which you would need an hour for in a few seconds, but ultimately you don't need it. And it says the object is, and you see here now the absolute, that is a Cosy command, ME12 gives you the R12, the focusing function. So you say, you take that matrix element, you add the absolute value, and you don't run into problems that it runs to infinity or something. So you take the absolute value, and you add the vertical function focus, which is R34. So if you change the angle, what does Y do? You add these two and consider that as the object. And with the fit command, and fit, it tells you, make that object, which is defined here, 10 to minus 5, to 10 to minus, precision of 10 to minus 5, in a maximum of 1,000 steps. It ended earlier, we didn't wait for 1,000 steps. And then there are several types of fits that you can make, a grid search, etc., etc. You have to look at the manual if you want something else. This is just one type of fitting algorithm. So you can fit. So maybe I make a stop here. I flooded you with a lot of information, and maybe you have questions. Yeah.
What's the first parameter in SB line? Is it the size of the beam?
If SB is a command, so you need to, you can look at the manual. I had written here that I skipped over that probably too quickly, but it was here. So this here is in the Cosy beam manual. You'll find that command like any other command, and it gives you, sets half the width of the beam in X, A, Y, B, T, D, and G. So we change, so this is the width of the beam. So 0.001 would be 1 millimeter because it's in meter. And this is the angle. So plus minus 0.025 would be plus minus 0.25 milliradian roughly. And then you have here an R12 element, which is the ellipse is in that case, if you make that 0, upright. But it could be at an angle. So you could start with some emittance at some point. If you start at the target, of course, you always have the upside emittance. So that, and then you have Y, phi, or YB, the cross term there. Then you have D, which is the energy. If you have an energy change, you could change the energy. In the quadrupole setting, I'm not changing here, but it doesn't help because the quadrupole doesn't care about the, in first order, about the dispersion. You would need a dipole. Okay?
So when you find the beam of 15 centimeters of width, right? But the plots with rays show that the beam begins from the point.
Yes, yeah. Well, there's, sorry, there's one more. There is one more, that the ER command. Don't I have it here? you saw there, good question. You saw here the ER command? The ER command takes that what I just said and splits it into 1, 2, 3, 4 subdivisions. So if you write 25 milliradian, then it would take, and you write 5, then it would 25, 12.5, 0, minus 12.5, minus 25. These 5 rays. If you write here 1, as I've written here, then it just takes a central ray. So I would have to show you the 1.15 centimeter, which I didn't want, and then I would make here 3, then I would get the 3, 5, then I would get the 5, and then you would see what you expected to see. So that is the control you have. There are many, this is not the best way of defining rays. You can program rays. For instance, in the Checker manual, you'll find that I defined my rays myself in an ellipsoid with equal grid in all dimensions. So I call them characteristic rays, so you can define yourself rays if you want. Or there's the SR command, which is a more simple ray for one ray. If you just want one ray to study the dispersion through the system or so, you may just want one ray and not all these rays in the SB command. So just to give you a hint, there are more ways to define rays than what I'm showing here. Any other questions? Yeah.
What does that map to unity? In the first example, there is a command which is UM to set the map to unity.
Yeah.
I don't know what.
Okay. The unity matrix is a matrix with all zeros except for the first diagonal. So if you take a ray, any ray, X, A, Y, B, and so on, and you multiply the unity matrix on it, nothing happens. You get the same ray back, the same X, Y, and so on. Just look through the matrix multiplication. Okay. Yeah, I said it, but let me repeat. If you don't put this command there, probably nothing will happen if you have your computer fresh. But if you're in a complicated system, you may already have a matrix stored in the map. So if you add now something else, it will say, take this matrix and continue on that matrix. Okay, just to reset the computer fresh from no other matrix, pre-existing matrix is affecting this calculation. You set this delivery to 0. That is like in programming, it is a good practice when you have a parameter and it will be calculated to set it to 0. You know, it may be 0 under certain circumstances, but in a complicated code, it may actually have some value and you didn't realize that. And then of course the result is wrong. So resetting a parameter in a code at the beginning of the code is a good programming practice, and that's equivalent here to setting the matrix to unity matrix. Setting it basically to 0, which is in matrix terms, do nothing. So it's a diagonal.
In the first example, you use 2 particles. One is with opposite signs for the field, but how do you distinguish between the 2 particles in reality? I mean, how do you know that? Okay, the first particle is for focusing, and the second one is for defocusing. How do you distinguish it?
Yeah. Well, it's defined in Cosy manual. It says if you have a positive pole tip, then this is focusing. Horizontally positive, then it's horizontally focusing. So now you need to look at a picture that I didn't have the time to show this morning, but I will show the next time to see. Oh, you can actually see it here. Well, maybe you see here. See, this is a horizontal plane. It is horizontally focusing. You see here, isn't it? This is horizontally defocusing. So that is positive. And how that in lecture one, you maybe do we have the time to do that? Quadrupole. Where do we have the lecture one? Okay. So you address the question, how do I see that the quadrupole is focusing or defocusing and what I need to do? This here is a quadrupole showing the North Pole, South Pole. So the field lines go like this, and they go like this, and they go like this, and they go like this from south to north. Now we know if you are, so here the field is like this. See, this here is in this plane, and the other way around here. Now you make the V cross B, which is the force on the, so if you make that, you will see that the force goes here. B is into the plane, the beam direction. So if you make V cross B, it's actually the other way around. Maybe coming. You see that the force is here to the right and on the left side to the left. So this quadrupole with North Pole and South Pole oriented like this is horizontally defocusing. And vertically, you have to take here the beam, the V, the velocity, and the B, and make a cross, make this screw rule, 3-finger rule, or whatever you want to call it, the cross product, and you see where the force goes. And then you see that vertically, this is the force vector, is vertically focusing. So if that's what you want, then you need to provide the North Pole and the South Pole. And in practical terms, you didn't have to worry what force south and north is. If it's going the wrong direction, you just reverse. Fernando knows that. You just reverse the input cables. There are only 2 cables coming into the 4 coils. There. Okay? And if you still have questions, Fernando knows all about what polarity you need. That is, for quadrupole, it's still easy. If you come to the hexapole and the higher orders, then you have to probably make a mistake for the first time. Get it second time right. Any other questions? The syntax, I didn't say much of the syntax, just to save some time, but you always need the semicolon at the end. So the command, and then the parameters, and then the semicolon. At the beginning, you will forget the semicolon when you add it, then the program complains of some bizarre thing. So there's some, you need some practice to figure that one out. And if you have questions, of course, obviously, I will help you with that. So, for? Delay. You mean delaying the calculation
Yeah.
or delaying the time? Not that. What can you do for delaying? That might actually be. I mean, Cosy is a very complex program, and I mean, as much as I'm considered to be an expert in these fields, you know, I even don't know everything. That's well, manuals for sometimes even the manual is, you know, it is such a way you never know it until somebody tells you, and then you find it in the manual, not the other way around, which would be preferable. So I don't know about the delay, but it may be. Why do you want to do? Oh, it was too fast. Yeah. Well, I don't know. By luck, the fit I showed you was that looked nice. Yeah. But of course, if that happens in a millisecond, then you're asking for delay. Sorry. Martin Berg should know, but I'm not sure he answers your email. If you yeah, not that critical. Any other? So have you been running some of the examples? Do they work for you too? Yeah. Oh yes, they are on the wiki. Yeah, maybe somebody else is faster to show you. Yeah, under lecture there. So if you go to the wiki, lecture series, link to tutorial files. You see here they are. For some reason, we couldn't upload the Fox file on the wiki. It maybe thought it's too suspicious. Extended Fox. So we had to zip it. So you have to download it and then unzip it and then run it. Yeah, I was of course prepared with my own directory already. That's why. Good question. Yeah.
In the fitting procedure, how does the program know that it should change the magnetic field instead of the, for example, reduce the length or the aperture or something like that?
Oh, what you have to do, what you have seen there, you have to say which parameters you fit, and these were Q1 and Q2. So these were in the command. I put in Q1 and Q2, actually was A and B. You'll see that command instead of a number. If you put in a number there, then of course it's fixed. The fit doesn't know. But if you make a parameter and then fit these two parameters with the objective to get the focus, which is ME12, which is a matrix element, which you know by now, to 0. So that is, and you can put in any parameter you want. But of course, if you would ask to change the time of day, then it wouldn't have any effect. So you have to know when you fit something, you have to know what doesn't affect. That's why I often, before I go to any fit, I go and change the parameters that I think have an effect. I eliminate all the negligible small things, and I take the main parameters that affect that what I want to fit the most, and then I run a fit. But that requires some experience when you look at the whole plot, that some experience which elements may fit. Now, of course, if you want to focus, changing the dipole will not help you. You will need to focus the quadrupole, that's obvious. Yeah. Yeah. Yeah, unless there are questions that I can answer right away. Yeah.